So, hi everyone, my name is Vedant Reddy and today I'll be talking about the topic semantic segmentation for the course image processing and computer vision. Uh, Hello, semantic segmentation is one of the most important tasks in computer vision where we aim to understand the content of the image at the pixel level. And this session will explore what semantic segmentation is, how it works, and how it performs using OpenCV and pre-trained models. This combines both image processing and deep learning concepts. Now, the overview of this lecture is to learn the basics of image segmentation, the types of segmentation, go through the traditional methods of segmentation and the modern methods such as deep learning for segmentation, and see certain implementation with OpenCV applications and some others. So, introducing segmentation or image segmentation. Every image we process has several objects such as road, cars, people, sky, animals, etc. Semantic segmentation helps identify what each pixel represents instead of just saying there's a car in an image. Like this, the car in an image would more be like object detection, but segmentation is gives label to each pixel value. It shows exactly which pixels belong to the car. We'll first understand how traditional image processing handled this, then move towards the deep learning approaches that achieve more accurate results. Image segmentation. In computer vision, there are multiple ways to understand an image. The first or the most basic step which we take in image processing is classification. Tells us what is in the image, like cat or dog. In this image, you can see like it identifies it as a cat because it is a cat. And then there's object detection, tells us where the object is by drawing a boundary box. Here, the box is very precise because it uses segmentation, but usually it would be like a rectangle or a square identifying where the object. And then comes segmentation, tells us which pixels belong to which object. Segmentation thus goes beyond detection and classification. It gives fine-grained understanding at pixel level. Now we know that now we know the basic definition of segmentation. Let's look deep into it now. In image processing, segmentation is about dividing an image into a meaningful region. We are not just detecting what is in the image, but also where it is. Semantic segmentation assigns a class label to every class or every pixel, like sky, road, car, or person. It's one of the key steps towards understanding themes the way humans do. Then let's look forward into the types of segmentation. Semantic segmentation, every pixel is assigned a class label, but individual objects of the same class aren't separated. Example, all cars in an image share the same label car. We'll look into the example in detail so you'll understand more nicely. Instance segmentation detects each individual object in an image. Even if they belong to the same class, they'll have a different table. Like two people in an image or two different cars in an image will have as label person one, person two, all card one card. And panoptic segmentation provides a complete pixel-wise understanding of the shape, combines both semantic segmentation and instance segmentation. This is the example image. You can see it's a crossway. You can observe many cars, many people, road, buildings, traffic lights, sky, trees, etc., etc. So when we feed this image in a semantic segmentation model or by doing thresholding or traditional methods, we'll see that semantic segmentation just like it broadly classifies everything into labels. Every pixel has a label. Like each pixel is having a label. Like this pixel has blue, which is car. This has red, which is person. This has purple or violet, which is road. And labels are divided into broader groups. Like it's a larger label. It's a, like background. You can see the building is one label, sky is one label, road is one label, car is one label. And nothing is neglected in the image. Everything is considered, and each and every pixel is labeled. Whereas in instance segmentation, you can see the whole background is neglected. It just sees the foreground and identifies the objects. And each object gets its own class. It's not like you can see cars of different colors. These all come under the class car, but they have different labels as car 1, car 2, car 3. Same goes for the person. And as you can see, the background is totally negative. Now coming to panoptic segmentation, it combines the best of the both worlds. It uses both semantic and instance methods. It doesn't neglect the background like instance. It'll take the background using the semantic methods, like you can see the road, buildings, and all are similar to the semantic segmentation, whereas the foreground objects are very similar to instance segmentation. Now, why do we need semantic segmentation? Like traditional image classification tells us what is in the image. Object detection gives us where the object are. So why do we need semantic segmentation? Like for the class for tasks like lane detection, tumor detection, or background replacement, we need a like very high precision or like pixel level precision. That's where semantic segmentation comes in. Classification and detection are just object oriented or very specific area oriented, whereas segmentation is broad, like it's at every pixel level. So we can identify each and every detail of the image. Moving on to traditional segmentation methods. Before deep learning and before CS convolution neural network, segmentation relied on basic image processing techniques. We can see like the common approaches were thresholding, edge detection, region growing, watershed algorithm. We'll look into each of them in the forward slides, in the next slide. However, these methods fail when the background is very complex. The lighting changes or color overlaps. You can see in this example images only, like the image is a very simple, not to say a very simple, but easy image. But since it's a broad day image, like the colored image was a very shiny and very changed, like you can see there's a lot of shadows and everything. So when it comes to edge detection, it doesn't perform that great. Now, about the thresholding technique, about the image processing technique. Thresholding is one of the simplest techniques. Divides pixel into regions based on intensity values, converts grayscale images into binary image like foreground and background. Global thresholding, one threshold value for the entire image, which you'll see in the next example, which is this. Like you just get one threshold value. So in this image, there's a certain background, buildings, grass, camera, and the guy. But after thresholding, you can see only the guy, the foreground is visible. Then comes edge detection. Oh, in thresholding, yeah, there is different methods such as adaptive thresholding also. Threshold changes across regions where there's uneven lighting or mainly used for difference in lighting where there are more shadows and more highlights. And there is also method automatically finds the optimal threshold by minimizing intra-class variance. Works well when object and background have distinct intensity levels. Moving on to edge detection. Detects boundaries between different regions in an image based on intensity gradients, like rapid changes in pixel level, which is basically edges you can see like when the color changes or whenever there's a change in a object, there will be a rapid change or difference in the value of the pixel. The very commonly used operators are Sobel operator, canny edge operator, even Laplacian operator is very commonly used. This Sobel operator computes gradient, magnitude, and direction, whereas Canny edge detector uses noise reduction, gradient computation, and edge tracking by hysteresis, which gives clean edges. Useful for shape detection and object outlines, but it's very sensitive to noise and illumination changes. In this example, you can see we have used Laplacian edge detection just to detect the edge of the lotus, and it's very like it's edge detection based. And then comes region growing. So region growing is a very simple algorithm, but yet very complex, and it's very simple in explanation or like in the concept wise, but it's very niche for the use. Region growing algorithm starts with seed pixels, one or more points that belong to a region. Then it grows that region by including neighboring pixels that have a similar properties, intensity, color, and texture. Like in this process, you have to manually select the seeds and then apply the threshold values and all, and after 4 or 5 iterations, or after many iterations each, like it will grow and it will take over a certain region and it will classify that region as one label. The advantages of this method are it produces homogeneous region based on intensity or color, very intuitive and very easy to implement, can be adapted to different applications by changing similar criteria. But the main disadvantage is it's very sensitive to noise. Like it can cause irregular region growth and depends on seed selection. Like if bad seeds are selected, it may cause bad segmentation. Then comes watershed algorithm. It's a very unique algorithm. It uses it uses topography basically, where pixel intensity is treated like elevation. Imagine a 3D image where the peaks are mountains, or the brighter areas are mountain peaks and the darker areas are valley. So when you pour water, like all the water will get, like it will cover the valleys, and then certain parts remaining above will be the mountain peaks and the slopes. So we can see that in the image, like they treat grayscale image as topographic surface, plus the surface starting from predefined markers and ridges from an object. It's very effective for overlapping or touching objects. It's basically gives the idea of distance from the camera, distance from the origin of light. Here you can see the foreground, like the first image shows that the white parts are for sure the foreground, or are for sure the peaks. Like this white region is always going to be the closer to the light or peak. Whereas in the second image, it shows the black region is for sure the background. Like you can consider that that is always the background. Like there's no overlapping in that. Moving on to deep learning based segmentation. Now, deep learning completely changed how segmentation works. Instead of relying on handcrafted rules, CNN learned patterns automatically from data. Now, the popular architecture used are fully convolution network is the first deep model for segmentation. UNet, SegNet, and Deep Lab, which is Google's model using dilated convolutions for hierarchies. Now, you can see the examples of the architecture of each. If this the first image is fully connected or fully convolutional network, is basically nothing but it uses standard convolution and pooling to extract features. Image resolution decreases, it reduces image resolution, and deeper layers capture more semantic meaning. And then when you and then there's a decoder in it. Instead of fully connected layers, it uses transport convolution, also called deconvolutions, to upsample the features. And the skip connections combines high level and low level features for summing them for earlier layers. Advantages are it's simple and effective baseline, works on arbitrary image sizes. The limitations are it struggles with fine detail and chorus boundaries are due to coding. Then we move on to UNet. UNet is mainly used for biomedical images or very microbiology images. It was based on same encoder decoder structure with symmetric skip connection. The encoder here is similar to CNN. There is convolution pruning, extracts features and reduces resolution. The decoder upsamples the features, maps using transpose convolution, very similar, but the main changes are in skip connection. Each step from encoder is concatenated, not added, to the corresponding decoder layer. This transfers spatial detail. This transfers spatial detail lost during pulling back to the upsampling path. The advantages are greater for small datasets and precise segmentation, like medical images, efficient training with few samples, but it's not ideal for very large or complex datasets, can be computationally heavy if input size is large. Then comes SegNet. It's again the same encoder decoder based architecture, but the encoder here is based on BGG16 convolution layers. It stores pooling indices, like positions of max values during pooling is stored in certain place. The decoder uses the stored pooling indices to upsample feature maps. This avoids learning large deconvolution filters faster and lighter. And then at final, there's a softmax classifier produces a class probability for each pixel. Here, the advantages are it's very lightweight and efficient, suitable for real-time and embedded applications. Limitations are similar to the fully convolution layer. Its coarse boundaries than unit and deep level. Yeah. So moving on, we have applications of semantic segmentation. There's mainly applied in autonomous driving, like to detect roads, lanes, pedestrians, vehicles, people passing by. And the other application might be medical imaging. It identifies tumor cells and organs. Here you could use unit, as I mentioned, and the autonomous driving you could use uh, fully connected layers or segment would be better. And satellite imaging distinguishing land, water, vegetation, or urban areas. Then there's on agriculture purposes, analyze crop health and soil pattern. AR/VR separate background and foreground for virtual overlays. Essentially, anywhere that pixel level understanding is required, segmentation is applicable or is. Now, in summary, or key takeaways, semantic segmentation assigns a class to every pixel. Traditional methods are simple but limited to basic images. Deep learning handles complexity, learns context, and produces reliable results. Using OpenCV and DNN modules, we can apply powerful segmentation models easily. This performs the foundation for advanced tasks like instance and panoptic segmentation. Thank you.